Welcome back. The objectives of this video are to study the sum of a finite geometric sequence. We'll also take a look at geometric series, and we'll give some samples of finding the sum of infinite geometric series. So we can find the formula for a sum of a finite geometric series in the following ways. Given our finite geometric sequence pattern that we previously studied, with a common ratio or r not equal to 1, we can find the sum of the finite series using this formula. The sum of n numbers of the sequence beginning at 1 to n is the sum of a sub 1 times r to the I minus 1 equals this formula, this pattern here. A sub 1 times the quantity 1 minus r to the n all over 1 minus r. If we're asked something like this, we want to find the following sum of 4 times 0.03 to the n from n to 12. So we're looking for the sum of 12 terms here. So writing out the first few terms, 0.3 to the first, 0.3 to the second, 4 times 0.3 to the third, 12 different times. Our a sub 1 is 4 times 0.3. Our r is 0.3. We've studied that before. That's our r. That totally makes sense. And n is 12. Now we can simply apply the formula for the sum of a finite geometric sequence. Our formula a sub 1 times the quantity 1 minus r to the n all over 1 minus r. So our a sub 1 is 4 times 0.3 times the quantity 1 minus r 0.3 to the 12th. That's our n times all over 1 minus 0.3. So we're just substituting values into our formula, input everything into our calculator, and we should get 1.71. When using this formula for the sum of a geometric sequence, we need to be careful to check that the index begins at I equals 1. Sometimes, as you see down here, we'll have n or I equals 0. Then you've got to adjust the formula for that first partial sum. Okay, so if we would have begun the previous sample with n equals 0, we would have had 4 times 0.3 raised to the 0. Anything to the 0 power is 1. So now we have 4 becomes our first term, and then from there we can figure out the sum after that using n equals 1 from 1 to 12. Our answer here would have then been 4 plus the 1.71 we got from the previous problem. The n equals 0, or that beginning term, really gives us the 4 and then added to the sum. Our second objective is to introduce geometric series, and the sum of the terms of an infinite geometric sequence is called an infinite geometric series, or simply a geometric series. And the formula for the sum of a finite geometric sequence can, depending on the value of r, be extended to produce our formula for the sum of an infinite geometric series. So we're going to use what we had before for a finite geometric sequence to help us find the infinite geometric series. Specifically, if the common ratio has a property of r is less than 1, we can show, and that's the absolute value of r is less than 1, it can be shown that r to the n becomes closer and closer to 0 as n increases without bounds. So this r to the n in an infinite geometric series, as n goes to infinity, welcome to calculus, approaches 0. So we end up with 1 minus 0 from our previous formula all over 1 minus r. Well, if you have 1 minus 0, then our numerator just becomes 1, which leads us to our formula for an infinite geometric series. And that has the sum from I at 0 to infinity of a sub 1 r to the I equals a sub 1, because that we had minus 0, so all over 1 minus r. So this, of course, is for the absolute value of r is less than 1. That's listed up here. And then a quick note here, when the absolute value of r is greater than 1, this series will not have a sum. So let's take a look at a couple samples. We want to find the sum of an infinite geometric series. So in sample A here, the sum from n equals 0 to infinity of 4 times 0.6 raised to the n. So we're going to use our formula a sub 1 over 1 minus r. And our solution for a is listed here below. So our a sub 1 is 4 over 1 minus our r is 0.6. So that becomes 4 over 0.4. If I multiply top and bottom by 10, that would eliminate my decimals. That becomes 40 over 4, which is 10. You could do this as a fraction if you wish. We could have 4 over 4/10. Division is multiplying by the reciprocal. So we have 4 times 10 over 4. And our 4 simplify. And once again, we get 10. For B, they just give us the pattern. 3 and then 3/10 and then 3/100 and then 3/1000. If we wrote those out, 3 plus 3/10, 3/100, 3/1000. Well, while r here, you may see that I'm multiplying each one of these by 1/10. 3 times 1/10 is 3/10. 3/10 times 1/10 is 3/100 times 1/10 is 3/1000. So my r here is 1/10. So our solution to this particular one, our first term is 3, so that's our a sub 1. Plugging it into our formula, a sub 1 divided by a minus r. We calculated the r just a moment ago to be 1/10. I'll rewrite that for you. So we have 1 minus 1/10, 3 over 9/10. Division is multiplying by the reciprocal, so I can multiply by the reciprocal 10/9. 3 over 9 simplifies to 1 over 3, and that equals 10/3, or if you will, the sum is 3.33. Here's a couple more samples. Find each sum. The sum of n from n equals 0 to infinity of 5 times 0.5 raised to the n. So using our formula, that would be 5 all over 1 minus 0.5. Simplifies that to 5 over 1/2. And that equals 5 times 2 over 1, or 10. And here, in sample B, we have 5, 1, 2/10, which is 1/5, and 4 1/100. So we can figure out our r here seems to be 1/5. So if our r equals 1/5, that's the same as 0.2, if you will. Our first term is 5. So again, this one is 5 over 1 minus 0.2, which is 5 over 8/10. If you like fraction form, 5 divided by 8/10 is the equivalent of 5 times 10 over 8, 25/4, or 6.25, 6 1/4. So that wraps up our introduction to finite and infinite geometric series and finding the sums of those. And you'll get some more practice with this when I see you in class.